next speaker. Well, our next speaker is Dr. Murphy Egwe. He will tell us
Yes,
about spherical. I apologize
yes.
if I mispronounced. He will tell us
Yes.
about spherical analysis on fuzzy Lie groups.
Oh, thank you.
Thank
Thank you
you.
very much. Yes. Today, I want to speak on spherical analysis on fuzzy Lie groups. Our interest, basically, is to analyze what has been done on classical Lie groups in the fuzzy settings. So my outline as seen on the screen, and we have some preliminaries, the fuzzy Lie property, fuzzy topological groups, then spherical functions on fuzzy Lie groups, and then some major results that will be announced. In this presentation, if you are given a locally compact Lie group and its Lie algebra G, we are interested and we're going to consider a fuzzy analog of G, which we denote as G subscript F, called the fuzzy Lie group. And then we construct a spherical function, a version which Helgason has produced in his famous book. Now, the concept of fuzzy sets and their properties cannot be overemphasized. They have generalized the classical sets, and so they have wide applications in different places, in engineering, in biomedics, in decision-making, differential equations, networking. In fact, name it, there are so many in mathematics. And so because of our time, a lot of people have worked on these concepts of fuzzy sets, fuzzy topology, fuzzy topological spaces. And then in recent times, Akram in 2018 published a book entitled Fuzzy Lie Algebras. And so from this concept, we tried to generalize and to look at what Helgason has done. In the real sense of it, he has, for example, you have a locally compact group G, and then you have the set of all invariant differential operators on G. You have a homogeneous space like this. Helgason has shown that the space of all invariant differential operators on G is commutative under convolution and even under composition. And so this space is a space from where we have solutions of these invariant differential operators to construct our spherical functions. For this purpose, we are supposed to say that, okay, let me just give a brief introduction. I don't want to dwell much on the fuzzy sets. This is how a fuzzy set is defined. Everything terminates in 1, 0. And so we can take the membership functions as usual. And then the operations on fuzzy sets are well known. I will not want to go to that. I will just deal with the spherical functions where we are going. These are basic operations. They are inverses. And then fuzzy vector spaces and fuzzy topologies are well known also. So we have, maybe I should just go down because of our time so that I will show us from fuzzy topological groups. These are fuzzy topological spaces, which are well known. Good. Given a Lie algebra, this is a definition of a Lie algebra. We want to define the fuzzy analog of these Lie algebras. For every Lie algebra, we have just for vector spaces, we have that this is bilinear, the Lie bracket is bilinear, skew symmetric, and the Jacobi identity is satisfied. So the spaces that we want to consider are Lie groups. So we want to consider some maps which are compatible with the topological groups. So I will look at, sorry, because I didn't know that the time will just be 20 minutes. Great. So this is a fuzzy topological vector space is a vector space over the field equipped with the topology sigma. such that these two maps are continuous. If we have a topological group, then we must have a fuzzy Lie algebra equipped with such topologies such that these maps are continuous. Now, if we have our topological group, we can look at it with a compact topological subgroup. And so we can have a homogeneous space of such. But if the topology is the Lie topology, then we have a topological Lie group. Now, let me show us what we need to construct our spherical functions. For this fuzzy Lie group, this is a fuzzy Lie group. If a fuzzy Lie is a C1C manifold, a C1 fuzzy manifold, such that this one is compatible and is differentiable, is fuzzy differentiable. So we now have what we need to construct our spherical functions. The invariant differential. Yes, my internet is going off and on. I'm sorry. I'm sorry about, okay, maybe I'll just move to the main result so that we can look, okay, these are the invariant properties of this differential operator. So, but those are the classical forms, and then the Lie algebra. This is the symmetrization map, which we use to prove the commutativity of invariant differential operators in the classical forms. But we have the fuzzy operator property, which we now want to show here. This is the result, this property of any function such that any function on G such that f and k, a compact subgroup of G, such that fxky, this k is from the compact subgroup of G, and x and y are from G. If any function f xky is given as fx, fy, in this, we call that function a spherical function. And so this integral property is actually what the spherical function satisfies, as shown by Helgason. This result is what we want to show in the fuzzy sense, using the fuzzy Lie group, which we have constructed. So the theorem, which is a major result from Helgason, is that if this is symmetric, it's a symmetric pair, and this is commutative, in sense of convolution, then this one is commutative, and this one, G, is unimodular. Now, this result has been proven by Helgason, but our own result on fuzzy Lie group, we first of all showed that the algebra of k invariant differential operators on the fuzzy Lie group is commutative. And the proof is just not mimicking exactly what Helgason has shown, but we have to first of all assume that it's a C1 fuzzy manifold, not unlike what Helgason has done. And then we describe all the vector fields in this form. If we do that, then we want to show that the invariance property holds, and we expand that using the first definitions. We obtain this one. So, and that is the first part of the proof. And then the major result, which I will now show us, is that if we have, this is a theorem, yes. This theorem is that if you let G be a fuzzy Lie group and K a closed subgroup of G, with F1 being C1 fuzzy manifold of this bi-invariant space, if we say that every function here is bi-invariant, then F is a spherical function on Fg, with F being mapped from here to C. Where this is where F maps to. And so our proof is not as straightforward. We let F be a fuzzy set on a fuzzy Lie group, G, F, and T here, we get a T-cut set. In fact, by a T-cut set, we mean a membership function which satisfies this condition if F and X are actually elements of this fuzzy Lie group, and F is T1, F of X is T1, and F of Y is T2, then that is taken from the T-cut set, then X belongs to FT1 and Y is FT2. These FT1 are membership functions of FT1, and these FT2 are membership functions of FT2. If this inequality holds, then we say these membership functions, this inclusion holds, and that implies that X is in FT2 because of this inequality. And so okay, so we have shown if we have shown this condition, then it means that we can actually pick K in the compass subgroup of FG, and that such that F of XY, which is this, is T0, and the integral of this is T1, and then XY is in the membership function of FT0, and KXY is in the membership function of FT1, for which we satisfy this condition. And this is the result that we have set out to prove. Now, another way of proving this result is by showing that F is positive definite. And with that, we can construct positive definite spherical functions on the group. However, in constructing this, we need to show that for every G and a compact subgroup of automorphisms, or a compact subgroup of G, we can look at what we call Gevin pairs. In these Gevin pairs, we can now look at the space such that if you take, even when you take G and a compact subgroup of G, you can look at the semi-direct product of G and K. And if you do that, you can look at a pair, say G and its semi-direct product group, and show that with positive definiteness, you can actually realize commutativity of such spaces, of such Gevin pairs. With that, we can now move to spherical analysis in the fuzzy sense. But for this work, I have only ended the proof of this theorem because we don't have much to show because of the time. I'm only limited to this. So I didn't want to go into the Gevin pairs because that will take me a longer time. It would have been part of this talk, but I have to stop here. Sorry for the interruptions of my internet. The electricity in this place now is so bad. So my modem is not fully charged. It's going off and on. My internet source is not fully charged. So thank you very much.
Thank you very much for the presentation and for joining us.